Imagine staring down a colossal mathematical puzzle. I mean, a polynomial equation so complex it reaches the 16th degree.
Yeah, that's pretty intimidating.
For centuries, finding truly exact answers to equations that complex has been, well, a huge challenge, often deemed impossible, really, without just settling for approximations.
And it wasn't just a feeling. Classical mathematics, things like Abel's theorem, they actually explain why getting those precise symbolic solutions was considered, out of reach for many of these big ones.
So, a really long standing barrier in algebra.
Definitely. A fundamental one.
Okay, well, today we're doing a deep dive into something that might just completely redefine those boundaries.
Hmm.
It's called Ezouidi's theorem.
Hmm.
And this innovative approach promises to unlock those exact symbolic solutions, even for polynomials that have traditionally resisted any kind of exact resolution.
So, our mission today really is to explore the power of Ezouidi's theorem. We'll demonstrate its capabilities by tackling a truly challenging example of that 16th degree polynomial you
Uh,
mentioned. We want to uncover how it manages to get around the limitations of classical methods, how it provides precise, solvable roots where other methods, well, they just can't.
Okay, let's set the stage then. Talk about this specific mathematical beast we're going to try and tame.
Right.
It's a 16th degree polynomial. And look, if you saw it written out,
Yeah.
it's long, lots of terms, big coefficients.
It's seriously complex. Px equals x to the 16 minus 16x to the 15 plus 120x to the 14. It just keeps going.
We'll definitely put the full thing in the show notes so you can appreciate the sheer scale of it.
And that complexity, that's exactly why the traditional methods hit a kind of wall.
Right.
When you're dealing with polynomials of this size, the typical approach often involves numerical approximations, methods like Newton's method.
Okay, so those get you close, but not quite there. Like finding the square root of 2, you get 1.414, maybe 1.41421.
Exactly. You get closer and closer, but it's never the square root of 2 itself. It's just a decimal approximation.
And it might have rounding errors.
It's inherently susceptible to rounding errors, yes. And this is critical because classical mathematics, especially Abel's theorem, tells us something profound.
Which is?
For polynomials of degree 5 or higher, there often isn't a general formula using only basic arithmetic and radicals, square roots, cube roots, things like that, to find the exact solutions.
So for many of them, finding an exact symbolic solution was considered impossible.
Using those specific tools, yes, simply out of reach. Abel's theorem basically said, look, you can't always solve these high degree ones with radicals.
It drew a line in the sand at degree 4, essentially.
Pretty much. For general solutions using radicals, it's a cornerstone of algebra, defined a major boundary.
Okay. So how does Ezouidi's theorem fit in? How does it challenge this?
Well, this is where it gets really interesting. Ezouidi's theorem introduces a fundamentally different approach. It explicitly excludes classical methods, including relying on radicals in the way Abel's theorem discusses.
Excludes them.
Yes. It states that even polynomials, which do have roots that could be expressed with radicals, can be solved exactly using this new method, contrary to the limitations implied by focusing solely on radical solvability in the classical sense. It reframes the problem.
So it's not just another way to approximate.
Not at
It's about finding the actual exact mathematical identity of the roots.
Yes.
Like getting square root of 2 instead of 1.414.
Precisely. That's the core promise. Ezouidi's theorem reveals these truly exact symbolic roots through a very structured recursive process.
Recursive, okay.
It's not about iterating closer and closer. It provides precise, solvable roots for polynomials that classical methods might label unsolvable in that exact symbolic form. It completely steps around those traditional limitations.
That's a huge shift.
Yeah.
Approximate versus exact. So let's peek under the hood. How does it actually work? How does it achieve this precision?
Okay. It starts by expressing the polynomial in a very specific symbolic form. Our big 16th degree equation gets rewritten, not fundamentally changed, but its coefficients are represented symbolically in a new way.
Like giving it new labels.
Sort of. We represent it as px equals by 16 pounds 0 cubed by 15 plus L1 cubed by 14, and so on, down to the constant term L15q. Here, L0q corresponds to the original coefficient 16, L1q is 120, and L15q is negative 12,000.
Just a different notation for the same coefficients,
Exactly. It sets things up for the next step.
which is the recursive part.
Right. The heart of the theorem is calculating a set of symbolic coefficients, let's call them L-1Q values, recursively.
Hmm.
These S values are derived directly from those LQ coefficients of the polynomial we just defined.
A recursive means each one depends on the previous ones.
Precisely. There's a formula to calculate each SK1Q. It looks a bit complicated on paper.
Can you give us the gist without the full formula? What are the key ingredients?
Sure. Think of it like this. The formula involves a sum of terms. Each term uses binomial coefficients, those C and R, KR things. They act like scaling factors, adjusting the contribution of different parts.
Okay.
Then there are terms like NR, which relate to the degree and powers of that first coefficient, L0Q. And crucially, it uses earlier LQ terms from the polynomial representation, so LR1Q. It means each new SES value is built methodically from the polynomial's own structure and the previously calculated Pythagoras values.
It sounds like a very careful chain reaction, where each link is forged using only exact symbolic parts.
That's a good way to put it.
And the key insight is no numbers are rounded off. It's all symbolic.
That is absolutely the key. Every single coefficient, every S value is determined symbolically. There are no numerical approximations, no floating point arithmetic, no rounding errors introduced at all.
Wow.
By design, this process guarantees the exactness of whatever results from it. It completely bypasses the approximation issues inherent in numerical methods.
Okay, so we have this monster degree 16 polynomial. We have this theorem with its symbolic representation and this exact recursive calculation.
Mm-hmm.
What happens when you actually apply the theorem to our specific polynomial? What do these Weary's values look like? Do we get the roots?
It's actually quite revealing when you apply Ezouidi's theorem and calculate these SK1Q values for our specific polynomial.
Yes.
You find a really interesting pattern. A whole bunch of them turn out to be exactly zero.
Zero, really? For such a complicated polynomial.
Exactly zero. Specifically, the coefficients from S0Q right through S6Q, and then again from S8Q through S14Q, all zero.
That simplifies things considerably.
It does. It means the structure is, in a way, simpler than it first appears when viewed through this lens.
Oh, wait, only 2 of them are zero out of 16 possible C's values.
That's right, for this specific polynomial example. Only 2 are non-zero, S7Q and S15Q.
And what are they? Are they simple numbers?
They are exact, but not necessarily small. S7Q calculates out to be negative 1,860 times 16 to the power of 8.
Okay, a large negative number.
And S15Q is 859 times 16 to the power of 16.
Whoa. Also huge, but positive. But the point is, these are exact integer values derived symbolically.
Precisely. No decimals, no about, no approximately. These are the exact symbolic results from the recursive process.
And from these as values, you get the roots.
These S values hold the key. They essentially encode the information needed to express the exact roots of the polynomial symbolically. The theorem provides the pathway from these calculated values to the final roots.
So this whole process demonstrates that for this really complex, high-degree polynomial, where traditionally you'd expect only approximations, Ezouidi's theorem delivers precise, solvable, exact outcomes. It tackles something deemed unresolvable with radicals by using a completely different symbolic framework.
Exactly. It's like finally finding the true name, the exact identity of the solution, not just a description or an estimate.
So thinking back, we just walked through a method that doesn't just, solve a daunting 16th degree polynomial.
Right.
It seems to fundamentally challenge some long-held assumptions in algebra about what's even possible.
It really does.
Ezouidi's theorem gives these exact symbolic solutions, overcoming those historical limits of approximation, and even tackling problems that seemed locked behind barriers like Abel's theorem, at least in terms of radical solution.
It's a powerful illustration, I think, that sometimes progress doesn't come from just refining old tools, but from inventing completely new ones, finding a different way to ask the question, mathematically speaking.
Yeah. This deep dive, it feels like a strong reminder that even in fields as established, as old as mathematics, new perspectives can totally redefine what we understand and what we can do.
Absolutely.
Which really makes you wonder, doesn't it? What other unsolvable problems out there, maybe in physics or engineering or computer science, might just be waiting for a new theorem, a new perspective, a new way of looking at the same old numbers to finally unlock their exact solutions too.